Look up at the night sky. What do you see? A vast expanse filled with stars, planets and galaxies. The universe is a place of incredible beauty and mystery. It's filled with questions that have captivated us for centuries. How did the universe begin? What is it made of? What are the fundamental laws that govern it? These are not easy questions to answer. Yet physicists have made incredible strides in understanding the cosmos. We have theories that explain the very large, like Einstein's theory of relativity, which describes gravity and the behavior of stars and galaxies. We also have theories that explain the very small, like quantum mechanics, which describes the bizarre world of atoms and subatomic particles. But there's a problem. These two pillars of modern physics, relativity and quantum mechanics, seem to disagree with each other. They offer different perspectives on the fabric of reality. This conflict suggests that we're missing something fundamental, a deeper understanding of the universe's workings. Enter string theory, a radical yet elegant idea that attempts to reconcile these seemingly incompatible realms. Imagine for a moment that you could zoom in on the tiniest building blocks of matter, far smaller than even atoms. String theory proposes that you wouldn't find particles at all, but something even more fundamental, tiny, vibrating strands of energy, called strings. Think of a guitar string. Depending on how it vibrates, it produces different musical notes. In a similar way, string theory suggests that the different vibrations of these fundamental strings give rise to all the particles and forces that make up our universe. One vibration pattern might correspond to an electron, another to a photon of light, and yet another to the force of gravity. To understand why string theory is so compelling, we need to look at the conflict between Einstein's theory of relativity and quantum mechanics. Einstein's theory describes gravity as the curvature of space-time caused by massive objects. It works incredibly well for explaining the motion of planets, stars and galaxies. Quantum mechanics, on the other hand, describes the universe as inherently uncertain and probabilistic. Particles can exist in multiple states at once, and their behavior is governed by probabilities. This framework has been incredibly successful in explaining the behavior of atoms, subatomic particles, and the forces that govern them. The problem arises when we try to apply both theories to extreme environments where gravity is incredibly strong and quantum effects are significant, such as the center of a black hole or the very beginning of the universe. In these scenarios, both theories break down, leading to nonsensical predictions. Section 4, String Theory, a bridge between worlds. This is where string theory comes in. By replacing point-like particles with vibrating strings, string theory offers a potential way to unify gravity and quantum mechanics into a single coherent framework. In string theory, gravity is no longer a force that acts instantaneously across space-time. Instead, it emerges naturally from the interactions of these vibrating strings. This unification of gravity and quantum mechanics is one of the most profound implications of string theory. It suggests that all the forces and particles in the universe, from the smallest subatomic particles to the largest structures in the cosmos, could be described by a single elegant theory, a theory of everything. Section 5. The landscape of the multiverse. String theory's implications don't stop there. One of its most mind-boggling predictions is the existence of extra spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions are thought to be curled up and hidden from view, much like a garden hose might appear as a one-dimensional line from a distance. The existence of these extra dimensions could have profound implications for our understanding of the universe. For example, some string theorists believe that our universe might be just one of many universes, each with its own unique set of physical laws and constants, a concept known as the multiverse. Section 6. The challenge of proof. Despite its elegance and potential, string theory remains a highly controversial subject within the realm of physics. The biggest challenge facing string theory is the lack of experimental evidence. The strings it describes are thought to be far too small to be detected by any current or foreseeable experiments. This lack of empirical support has led some physicists to criticize string theory as being more philosophy than science. They argue that without the ability to test its predictions, string theory remains purely speculative. Section 7. Toward a deeper understanding, despite the challenges, string theory continues to be an active and exciting area of research. Physicists are developing new mathematical tools and techniques to explore the theory's implications and search for ways to connect it to observable phenomena. While it remains uncertain whether string theory will ultimately prove to be the correct description of our universe, it has undoubtedly enriched our understanding of the fundamental laws of physics and pushed the boundaries of human knowledge. The search for a unified theory of everything is a testament to our innate curiosity and our desire to comprehend the cosmos and our place within it. The journey toward a deeper understanding of the universe continues.